Swayam Prabha. Digital India. Educated India.
Hello all, welcome to Astrochemistry. This is lecture 41. Now recall that the last few sessions were tutorial sessions. I wanted to tell a few things in the last tutorial sessions which I had forgotten. Just one or two points about the Schrodinger equation itself. That is, so two pending points, right? I wanted to discuss from the previous tutorial, that is from lecture 40. The first point is that, note that, we looked into the time independent Schrodinger equation and the time dependent Schrodinger equation, right? Now, in our discussion, in our brief discussion, quantum mechanics is an ocean and we did not even touch the surface, right? In our brief discussion of quantum mechanics, QM, that is quantum mechanics, as needed in this class, right? As needed for Astrochem in this class, right? This class. Right? We looked at these two equations. H psi equals E psi, which is the time independent Schrodinger equation. And we also looked at right? We looked at H psi equals I H bar dou psi by dt. This is the time dependent Schrodinger equation. Now, common to both of them, right? While we were briefly discussing both of them, briefly and succinctly, we did not go into too many details because this is an astrochemistry course and I have to cover so many other aspects, right? Now, I H bar dou psi by dt is H psi and H psi equals D psi are TISC and TDSC respectively. But note that they do not contain information about, they do not contain any information about two very important aspects, right? In physics and chemistry and also astrochemistry, therefore, the spin of an atomic system or a molecular system, right? Remember, you must be studying about the spin of an electron, you must be talking about plus half, minus half, the spin quantum number, etc. in your 11th and 12th standards onwards, correct? Now, the discussion of the Schrodinger equations, they did not include any aspects about the spin of any molecular system, right? As well as relativistic effects. So, our discussion completely excluded both these aspects. Now, I just wanted to bring this up in the last tutorial itself, but then I forgot to mention it. So therefore, I'm adding these 2 points precisely here so that your understanding is complete in the sense that we not just know what we have discussed in the class, but we also know what we have not discussed and why we have not discussed. Now these are introduced independently. Both spin and relativistic effects, naturally come about from what is called as the Dirac equation, right? But that is something beyond the scope of this course. All right, so this is point number 1. And the next point is, recall that we were looking at the free electron. The free electron problem, taught us about an energy expression, and then we restricted its flow, right? And subsequently, So subsequently, we restricted the flow of the electron, correct? We had a free electron and then we restricted the flow of the electron to understand that we get quantization due to boundary conditions. And it is due to this quantization that we get discrete spectra, and based on the discrete spectra, we can detect molecules in space. Okay, that was the bigger picture. Now the idea is this specific quantization, right? And by restricting the motion of the electron, we only look from x equals 0 to x equals L. Okay, right? We did not even discuss what would happen for x less than L, right? For x less than 0 and x greater than L. Please note this. It is not that, the problem, once we restrict the motion, the electron, and then by learning about the electron, we only get insight from this region only. For the purpose of this class, we restricted our discussion from x equal to 0 to x equal to L. However, there is a lot of information to be gained by learning about what happens in x less than 0 and x greater than L, right? We get information about a very important phenomenon. I'm just throwing in a jargon. Don't worry if you don't understand it. I'm just telling you that by studying the electron in this region, we get information about what is called as tunneling. Okay, right? What is tunneling in quantum mechanics and what is its significance? Again, I insist, I'm only using the phrase tunneling, right, without explaining what it means or what it does. And it's of course important in the context of astrochemistry. And when we actually go to the module on astrochemical reactions, we might, if we have the time, look into tunneling. Okay, so please note 2 points. One is that the Schrodinger equation that we discussed is not going to be a complete representation giving you all universal truth. Okay, it even that misses a few aspects, such as, for example, spin and relativistic effects, point number 1. And point number 2 is we only discussed the electron's restricted motion to understand quantization in the region x equal to 0 to x equal to L. We never understood what happened beyond it. Just because we restrict the motion of the electron from, let's say, 0 to L, it doesn't mean that we can get insight by ignoring the other regions. Okay, there is a lot of insight to be gained by studying this region also, but for the sake of time, right, for going back to some of the more direct aspects of astrochemistry, we have left it for study at a subsequent point in time, if time permits. All right, so please note these 2 points. With these 2 points clarified, I shall now comfortably begin the subject of today's lecture. Can you guess what is it? I have been talking about this for a long time, right? In fact, for about 5 or 6 or 7 lectures even now. What is it that we are going to discuss today? It's going to be the interaction of light with matter. All right, so we shall be discussing about how light interacts with matter. Okay, so effectively, light is a form of energy. This we have been seeing since primary school, in fact, right? Yeah. So when some matter in the context of astrochemistry, when we say light is interacting with matter, light is a form of energy that interacts with matter, and we shall be discussing it especially as relevant to astrochemistry, as needed for astrochemistry. Okay, so in other words, what does it mean by as needed for astrochemistry? I'm talking about what happens when light hits, electrons, atoms, and molecules. Matter for our purpose is going to be atoms and molecules, which comprise of electrons and nuclei. Okay, right? So that is what we're going to be concerned with when we study the interaction of light with matter. Okay, now, what do you think is the first thing that can happen when light interacts with matter? I'll give you a hint. The hint is, recall what happened when we detected what was present in sun using the Fraunhofer lines. What was happening there actually? The answer is that when light interacts with matter, a lot of things can happen. The first thing that can happen is what is called as absorption. Okay, so now what happens when light is absorbed, right? What happens when light is actually absorbed? We discussed, using the phenomenon of spectroscopy, recall, right? We started discussing about molecular translation, rotation, vibration, and going on to a higher electronic state, right? Now, what happens when light absorbs is that when light is absorbed by an atom or a molecule is that the molecule goes to an excited state from a ground state. Are we clear? So what happens is a molecule from its ground state, I'm going to call GS, right? To denote ground state of an atom or molecule, and I'm going to indicate, I'll put it this way, GS, and you supply it with some light, right? Light is denoted by h nu to indicate that a photon of energy is being absorbed by this ground state. Are we clear? So this is light, and this is the ground state of an atom or a molecule, and this is going to be excited state. We don't care about whether it is a rotational excited state or a vibrational excited state or in any new electronic excited state. It just happens that the minute you shine some light on an atom, right? It is going to get excited from the ground state to excited state. All right, this is the first phenomenon that could happen. Point number one. What is the next thing that could happen? Also note one more point before we proceed to the next aspect. It is that, do we really worry about whether it's translational, rotational, vibrational, or electronic? For currently, we don't care. It just gets excited, and can it also happen to be a translational excited state? The answer is yes, but that particular transition, that is from a translational ground state to excited state, we're not going to be getting much information because translation and energy is pretty low. The translational excitation energy is going to be pretty low, so we don't care about it. But from rotational, vibrational, and electronic states, we'll be getting useful information about what molecule it is. Recall the whole discourse on quantization and all that from the previous discussion. Okay, so I hope that aspect is clear to you. That said, after absorption, what can happen? The atom or molecule is now in its excited state, some excited state. What can happen to it afterwards? It has to come down, right? It has to come down. Now, why does it come down? From the excited state to the ground state. Why does it come down? Because thermodynamics dictates that you cannot be staying in an excited state for a long time. Okay, we haven't discussed thermodynamics in this specific course. We shall look into it, as part of some other course. Okay, now, as part of some other lecture in the same course. Okay, but now please take it for granted that once an atom or molecule is in its excited state, it has to go back to the ground state. This is based on the principles of thermodynamics. All right. So now this phenomenon of the atom or molecule being in the excited state going back to the ground state is what is called as spontaneous emission. Right? Now what happens in spontaneous emission? A molecule or atom in an excited state, right, goes back to the ground state, and the photon is emitted in this process. Are we fine with this? Okay, so we have absorption of light and emission of light, right? Absorption of light, which leads to a molecule going to an excited state, and we have the emission, which is spontaneous. Why is it spontaneous? It is spontaneous based on the laws of thermodynamics, and I haven't told you more details as of now. We'll discuss it either in a tutorial or when we discuss the thermodynamic aspects subsequently. Are we good, right? Okay. Now, the next point is, what else can happen? What else can happen, when light absorbs, when light is absorbed by matter? Here is something very interesting that can happen. Okay, I will tell you its name first, and I'll explain what it is. It's called stimulated emission. Now, See, let's say that, here in the ground state, a molecule is interacting with a photon, right? But, which is like basically some light of a specified energy, correct? Now, the molecule in the excited state can also actually interact with some photons, right? In other words, any excited state, based on the laws of thermodynamics, is of course going to fall back to the ground state. However, right, that phenomenon need not always be spontaneous. It can also be stimulated. It can also be stimulated by a photon, right? By a photon whose energy exactly matches the gap between the ground state and the excited state. Okay, right? In other words, your excited state, your excited state can be, like interacting with a photon, and that can therefore go to the ground state. Are we clear? Right? The difference between, your spontaneous emission, the difference between a spontaneous emission and your stimulated emission is that spontaneous emission happens as such. Okay, spontaneous emission happens without the interaction of the molecule or atom in the excited state with any photon of light. But in stimulated emission, what happens is a photon, a photon actually interacts with the excited state, and due to the interaction, it falls off to the ground state. Okay, are we good? Right? It falls off to the ground state. Now, there are some more details about stimulated emission. Okay, in fact, it should be said that this whole concept of stimulated emission is what is responsible for the development of this technique called as a laser, right? The whole principle of laser is based on this idea, and there are also some criteria for this, the photon. For example, the photon absorbed and the photon emitted should be in the same direction, etc. Those details we can be looking into a tutorial. For now, just understand the difference between spontaneous emission and stimulated emission. All right. So when light absorbs with, when light interacts with matter, these three things can happen based on our current understanding in this class. Okay. Now, here's something profound. Okay. Here's the beginning of something profound. It is that connecting these three aspects, we're going to call absorption as, say, something like abs, and I'm going to call spontaneous emission as spont. Please, get these abbreviations because we'll be using them often. And this is going to be called as stim. Okay, right? Now, these three phenomena, that is absorption, spontaneous emission, and stimulated emission, right? All these three phenomena, right? Connecting all these three, that is connecting abs, spont, and stim, right, is going to give us powerful knowledge about the intensities of spectral lines. Are we good, right? So connecting these three aspects, absorption of light, the spontaneous emission of light, and the stimulated emission of light, connecting all of them is going to give us very powerful knowledge about how, the intensities of the spectral lines are going to be. What's a spectral line? A spectral line is whatever is obtained as I plot the intensity of the line obtained from either from space or, from a sample on Earth versus some wavelength, wave number, or frequency. Correct? I have already told you this, recall. Okay. So by understanding the intensities, we can actually understand how much of molecules are present in any given sample. The sample can be on Earth, or the sample can also be extraterrestrial. That is what is obtained from space. All right. Therefore, understanding the connection between these three processes, right, is very important. And that is what we're going to do next. Okay. It's exceptionally important in the context of astrochemistry and spectroscopy. Okay. Now, before we do this, right, can you guess who was the person who actually made the very first connection between these three terms? You know this person, as a very prominent scientist, but you might probably not think about this person in this context. Who is this person? It turns out to be Albert Einstein. Okay, the same Einstein of the relativistic effect fame, the same Einstein of the photoelectric effect fame, the same Einstein, of the gravitational forces fame, right? Has also made tremendous contribution in astrochemistry and spectroscopy. I want to, just inform you this. So, how did Einstein connect all these three? That is what we shall be looking into as part of the next module in this course. Now, the first things first, okay. So I've already told that like ABS is absorption and SPONT is spontaneous and STIM is stimulated. Now note one more thing. So, when I say that an atom or molecule, right, goes from its ground state to excited state, what happens to the atom? Is it typically the nuclei that go to the ground or excited state? It's the electrons, right? It's not the nuclei, because, to break the nuclei requires a lot more energy. That is what we discussed as part of the nucleosynthesis, Big Bang nucleosynthesis, as well as in a tutorial where I told you the differing magnitudes between breaking electrons versus breaking nuclei. Okay, so when I say that, when an atom or molecule goes from the ground state to the excited state, it is the electron, right? I'll write it down. So any transition, right? Any transition in a molecule or atom between the ground state and excited state, right? I'm just calling them GS and ES, right? Involves the movement of, or we can say movement or transition, right, of electrons between the two states. Okay, that's important. So therefore, right, all your phenomena, all your ABS, that is absorption, SPON, that is spontaneous emission, and STIM, that is like stimulated emission, they all depend on the number of electrons that are present, right? So let us denote N1 to be the number of electrons in the ground state. Okay, and let N2 be the number of electrons in excited state. Okay, are we clear? Now, when we consider absorption first, okay, so considering absorption first, right, the rate, okay, now please notice that how can we quantify either of these absorption or emission phenomena? It can be quantified by understanding the rate of absorption. What do I mean by rate of absorption? It refers to the change in the number of electrons from the ground state to the excited state. Okay, right? Now, I can always quantify my absorption, right, or emission based on the number of electrons. That is what I said. Okay, right? I just repeated myself. Okay, which is good in the classroom because you get to understand, you get to hear about the same statement twice or thrice. Therefore, affirming that I'm indeed saying the same thing multiple times will be very helpful in cognition overall. Okay, so when considering absorption, right, let dN1, right, be the number of let Bn be the change, okay, change in number of electrons from ground state to excited state, right, over a period dt. Over, when you say period, it refers to time, okay, over a time period dt. Okay, so therefore, this understood, the rate of absorption, okay, the rate of absorption is given by dN1 by dt. Are we clear, right? What's always a rate? A rate is nothing but a change in some number over some time period. Okay, right? So this is going to be dN1 by dt. But also recall that, now this is going to be, the rate of change of electrons in the ground state. Okay, I'm just going to call this as abs to indicate that I'm talking about absorption in particular. But when the electrons, go from a ground state to excited state, the total number of electrons in the excited state are also going to be affected, right? So now, as part of absorption, okay, as part of absorption, we can write the rate of absorption in terms of the ground state, that is dN1 by dt, or the rate of absorption. I'm just going to call this like ROA, right? ROA, to indicate rate of absorption. Your rate of absorption can also be expressed in terms of excited state. Notice that this is the rate of absorption expressed in terms of ground state, via ground state. But the rate of absorption can always be expressed in terms of the excited state also. How do we do this? Simple. Instead of, choosing dt is going to be the same because we're talking about the same time period. But instead of letting it be dN1, I can always let it be dN2 as dN2 by dt. Are we clear? Right? So in terms of excited state, the rate of absorption is going to be dN2 by dt. We're fine, right? Now, as the electrons get absorbed, I can express the rate in terms of either the ground state or the excited state. However, note a caveat. It will be very useful for me. If, I define the rate in a unique way. Such that I can interconvert between this number and this number. All right. Now, say for example, if I have the condition, that my dN2 by dt is equal to negative of dN1 by dt. In other words, right, all the electrons that are getting to the excited state, are only coming from the ground state. Of course, the electrons are going to be in the excited state always, okay, right? But as part of this absorption, right, all the electrons in N2 are only coming from N1, okay, right? As part of this absorption, right, if I have this condition, then I can define a unique rate, okay? I can uniquely, that is, either by choosing dN1 or dN2, I can uniquely define the rate of absorption. Are we all good? So what did we do so far, right? I first introduced in this class. I'm just summing up now because it's almost close to 30 minutes. Okay. So we looked at what are the possible phenomena that could happen when light interacts with matter. When I say matter, I'm talking about an atom or molecule. We discussed what absorption meant, what spontaneous emission and what stimulated emission meant. And after that, we're trying to connect these three aspects. As part of it, I've introduced two terms called as dN1 by dt and dN2 by dt, where N2 is the number of electrons in the excited state and N1 the number of electrons in the ground state. All right. Now that said, we also saw that because the number of electrons in the excited state as part of the absorption are only coming from the number of electrons in the ground state, and because the directions are opposite, I have the expression dN2 by dt is equal to minus dN1 by dt as part of this absorption. All right. Now please note that because I have this, right, because I have the connection between dN2 by dt and dN1 by dt, which are related as just multiplying each other by -1, right, I can now uniquely define a rate of absorption, either in terms of N2 or in terms of N1. All right. So that is what we've done in this lecture, and we shall continue from here in the next lecture. Thank you so much.